So now that we know how to find antiderivatives, I want to go through how we would apply this to the definite integrals now. So how we can actually solve some of the definite integrals. So again, I just want to go through a bunch of examples basically, and I encourage you to do a lot of examples with these. Integrals are important and they can be really tricky. We'll see, these ones are relatively straightforward because we just have a couple formulas, but as we add on the techniques, they'll become kind of trickier and trickier, but they're very important. Okay. Like I said, like I've mentioned before, in probability, finding the probability of something with a continuous random variable is an integral. Finding the mean of something is an integral. So it pops up all over the place in stats. So it is very important to know how to do these. So, we can go ahead and just start with the one that we already did by hand, right? We did this one as using the definition, the limit definition. So let's do it using this definition now. Okay. So first of all, the antiderivative of x squared would be x cubed over x, or over 3. Okay. Now the way we usually write this, remember that by the fundamental theorem of calculus, this is equal to f3 minus f0. Okay. So the way we normally will write this is that we'll put a vertical bar here and then write the limits of integration on here to kind of say what numbers this needs to be evaluated at. Okay. So this is going to be equal to this when x equals 3. So 3 cubed over 3 minus this when x equals 0. So 0 cubed over 3. Okay. So again, that's from the fundamental theorem of calculus right here. So the antiderivative at 3, which is this part, minus the antiderivative at 0, which is this part. Okay. So 3 cubed is 27, divided by 3 is 9, and this part is just 0, so we just get 9. Okay. Okay. So we'll just keep going, just keep doing a few. I'll just do a bunch of examples here of different things that can come up. So -2 to 3 of t plus 2 times t minus 3 dt. Okay. Now, there's no rule about the product of integrals, right? We can't take the integral of these separately as a product. So we need to simplify the inside first. We need to multiply that out. Okay, so that's going to be t squared plus 2t minus 3t, so minus t, minus 6 dt. And now when it's just addition or subtraction, we can break that up. So we can do it all on one line. We don't have to write it all out separately. So this is going to be t cubed over 3 minus t squared over 2 minus 6t. And then these will all be evaluated from t equals -2 to t equals 3. Okay. So this is going to be 3 cubed over 3 minus 3 squared over 2 minus 6 times 3. And then minus, maybe it's good to put this in parentheses because you're subtracting the whole thing, -2 cubed over 3 minus -2 squared over 2 minus 6 times -2. Okay, so just I want to be careful with all the signs here. Just take it step by step. So that's 9. This is 9 over 2. So we'll just leave it as a fraction for now. This is 18 minus -2, or yeah, let's just do the whole thing on the inside first. -2 cubed is -8. -2 squared is 4. Divided by 2 is 2, and we're minusing it. -6 times -2 is plus 12. Okay. I apologize if I make an arithmetic error somewhere here, because there's just so many pieces that, it's very prone to doing that. So, let's see here. So we'll try to combine. So we got -9 minus 9 halves plus 8 thirds. This is 10, and then we're minusing it. So minus 10. So we have -19 minus 9 halves plus 8 thirds. We could probably just leave it like that. I mean, at this point, you can just throw it in a calculator, or you can find a common denominator. I'm never super worried about the exact answer, just about the process here, right? So at this point, you just throw that in a calculator. Assuming that we didn't make any arithmetic errors along the way, of course. Okay, here's an interesting one. Sometimes they'll write it a little bit strangely. Okay, so this one, the way it's written is as dt over t to the 1/4. Okay. So this is the same thing as 1 to the 16 of 1 over t to the 1/4 times dt. But dt, it does represent a physical quantity here. So sometimes it'll kind of be like, okay, 1 times dt is dt, and then they'll put it on top. So just know that these are the same thing. So other than that, this is just a straightforward power rule, right? T to the -1/4. I keep saying equals, but this is going to be t to the 3/4 over 3/4, which is 4 thirds t to the 3/4. So this is going to be 4 thirds t to the 3/4 from t equals 1 to t equals 16. So 16 to the 3/4 is going to be 8, right? The 4 through to 16 is 2, and then cubed is 8. So this is 4 thirds times 8 minus 1 to the 3/4 is just going to be 1, so we'll just minus 4 thirds. So this is 4 thirds times 7, so 28 thirds. Okay, just combining like terms there. Okay, so now let's look at some with absolute values. Okay. These actually come up kind of a lot in like theoretical probability, because often you need the expected value of the absolute value of x to be like less than infinity or something like that, just for certain things like some type of like law of large numbers and stuff like that. So just to say, it does come up in Proven Stats, so it's important to know how to handle things like this. And the way we handle it is actually based on its definition as a piecewise function. Okay, so remember, absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So this is exactly how we can handle it. We can break it up at that breakpoint. We can break up the integral at 0 because we have that property that lets us do that. So this is going to be equal to -2 to 0 of negative x dx plus 0 to 3 of x dx. Okay, and you could do this with any piecewise function as well. So absolute value functions are piecewise functions, so that's why we can do it here. But just in general, you can do this with any piecewise function. Okay, so we break it up at that transition point, and we look at those two pieces separately. Okay, this function it's still continuous, so there's no reason that we can't do this. So, and do keep in mind, you do need it to be continuous for the fundamental theorem of calculus to apply. So I guess I shouldn't say you can do it with any piecewise function, just the ones that are continuous. All right, so anyway, if we do this, then we have two separate integrals. So negative x would be negative x squared over 2. And we're evaluating that from x equals negative 2 to x equals 0. And then x is x squared over 2. And that's going from x equals 0 to x equals 3. Okay. So we'll go ahead and do all this. So negative 0 squared over 2 minus negative 2 squared over 2. We're really careful about all the negatives here. So that's the first one, plus 3 squared over 2 minus 0 squared over 2. Okay, so this is just 0 minus a negative. These cancel out. Negative 2 squared is 4, so that's just 2. This one is 9 halves. Okay, so 9 halves is like 4.5, so this is 6.5. Okay. And we could actually verify this one if we wanted to, because this does just make a triangle. So we could verify this one geometrically, which is nice to do when we can, right? So this goes up to 3, and then negative 2 goes up here. So this is a triangle with height 2 and width negative 2. And this is one with height 3 and width 3, right? So this one is going to be 1/2 times 3 times 3, so 9 halves. And this side is going to be 1/2 times 2 times negative 2, so negative 2. Oh, and I'm sorry. This should be a positive 2, because even though it is on the negative x's, we're still going to the right. Like we're going from negative 2 to 0. So that still makes it positive. The sign of this is about the direction, not about the side. The sign of the height is about whether you're above or below the x-axis. Okay. So yeah, so this should be positive still. So that's why we do end up with 6.5. Okay. Okay, now we can do a bit of a trickier one using the same idea here. What if we do negative 2 to 4 of the absolute value of t squared minus 2t minus 3 dt? Okay. So first of all, we need to know what the absolute value of this function is, meaning like where is it positive, where is it negative? Okay. So that means we need to find the zeros of this function. Okay, so we're going to have to do a little more work here. Okay, so this is equal to 0. We can factor this as t minus 3, t plus 1. So this is t equals 3, t equals negative 1, and then we can do a sign chart to see where is this positive and where is this negative. Okay, so if you plug in 0, you get negative 3, and then it should alternate from there. So this means that this t squared minus 2t minus 3 is equal to the positive version of this if t is less than negative 1 or greater than 3. And it really doesn't matter which side you put the equals to on, because at that point it's 0. And it's negative all this if it's between those numbers. Okay. So when we're looking at our limits of integration, we can see that it's getting into all three of these regions, right? So negative 2 to 4 were our limits of integration here. So let's just rewrite it down here. Negative 2 to 4, t squared minus 2t minus 3 dt. So this is going to be negative 2 to 1, or negative 1, of the positive version of this. Plus negative 1 to 3 of the negative version of this. You could just subtract this too. You could pull that negative out because that's a constant. So that might make it a little easier. And then you can, then we add on 3 to 4 of the positive one again. Okay. So this way we really only need to find the antiderivative once. So that's going to be t cubed over 3 minus t squared minus 3t. Okay, from negative 2 to negative 1. We don't always write the t equals part here if it's clear what the variable is. Minus the same thing from negative 1 to 3. And then plus the same thing just making sure I have all my signs right here. From 3 to 4. Okay. So we get negative 1 cubed is negative 1. Negative 1 squared is 1. This will be a positive 3. Minus, we plug in negative 2 here, so we get negative 8 thirds minus 4 plus 6. Okay, now we do minus 9 minus 9 minus 9. And maybe I should put this whole thing in a bracket and this in parentheses, because then we're doing minus negative 1 in there. So negative 1 third minus 1 plus 3. I'm definitely going to have to check my work here, because there are a lot of moving pieces here. 64 over 3 would that's not divisible, right? So minus 16 minus 12, and then minus, plugging in 3 now, 9 minus 9 minus 9. Okay. So I'll go back and make sure I didn't make any mistakes on this, and I'll update at the end if I did. I'll just roll with it for now. So this is 2 minus 1 third, which will give us 5 thirds. All right. This is 2 minus 8 thirds. Which will give us negative 2 thirds. Which will cancel with that other negative. And then minus 9 minus 9 minus 9 is negative 9. 2 minus 1 third again is 5 thirds. Negative 16 minus 12 is negative 28. So we get 64 thirds minus 28. And then minus a negative 9, so plus 9. Okay. Okay. So I skipped the end here so that you can, you don't have to watch me convert all these fractions and all that. Again, if you want, you can always just put in your calculator as well. But we do end up getting 46 thirds as the final answer here. So again, the important thing is breaking this up at the limits of, with the limits of integration at the different transition points for the absolute value function.